This. Okay, preparing to live stream the meeting. See the bar's going. Okay, I think we are now streaming live on YouTube, so apologies for that delay. There was an excellent introduction. If you want Bob Nairn's bio, it is linked on the Center for Wetlands website page under seminars. But instead of doing that again, I'm going to turn the floor over to Bob. And Bob, the floor is yours, and thanks for coming today.
Thank you all very much. And thank you so much for inviting me to speak with the Odum Wetlands Center. I'm going to ask, before I delve into the what I think is exciting work that we've been doing in Oklahoma, I'm going to ask for your indulgence for just 1 second. I did my graduate work at Ohio State, as was mentioned. And if you know the Ohio State Wetlands Program, and if you're familiar at all with the Olentangy River Wetlands Research Park, I was one of the first dissertations that was done there. Then you probably know who Bill Mitch is. And I just want to say that, I want to honor Dr. Mitch. He was a University of Florida grad, 1975, worked with H.T. Odum as his advisor. He passed away about 2 weeks ago. Bill was an amazing wetland scientist and ecological engineer, a prolific author, not just the textbooks that many of us are familiar with, but his refereed publication record is outstanding. His accolades are really too numerous to mention. He was a mentor and a friend to me. So I'm just going to ask those of you that obviously have some interest in wetlands, the next time you're out in the field and you find some truth and beauty in the environment, I ask you to think about Bill and all he did for helping to save our planet. I also would like to recognize that the University of Oklahoma resides on the lands of the Caddo and Wichita nations, and was a migration route and hunting ground for many other Native American tribes. Today, Oklahoma is home to 39 Native nations as a result of settler and colonial policies. And the university certainly recognizes the historical connection of our university, the land on which we live and work, with those indigenous communities, and recognize, support, and advocate for the sovereign rights of all of Oklahoma's 39 tribal nations. So with that said, I'm going to talk about wetlands today. So I'm not going to talk about wetlands that are quite as beautiful as this one on the screen. I'm going to talk about wetlands at a Superfund site. But this example, these beaver pond wetlands at a TNC preserve here in Oklahoma, are amazingly diverse, both from what you see visually, the plant life, etc., but also within the soils, the microbiological, biogeochemical actions that are occurring within the soil profile, within the water column, within the plants. And those things that wetlands do that provide those ecosystem services back to society that we so much value are things that we've attempted to mimic in some human-made systems to address some particularly challenging water quality issues. We think about infrastructure, and I think when we think about infrastructure, we think about roads and bridges and airports. We might think about wastewater treatment plants like this one. This is the City of Norman's water reclamation facility. Although this is an activated sludge plant, it's got a lot of biology that goes on in there, but there's a lot of fossil fuels, there's a lot of steel, there's a lot of concrete. This is more traditional infrastructure. And today I'm going to ask that we think about natural infrastructure. Before I move from this slide, I do want to point out down here in the corner, you see some little tanks on the surface. That is a wetland mesocosm compound that we built just a few years ago with some National Science Foundation funding, where we're examining different types of hydrologic designs to address emerging contaminants. So some of these non-regulated constituents in wastewater and urban stormwater. I think carrying on some of the mesocosm scale work that Odum and that Mitch did. But I'm not going to talk more about that today. But if this is our approach to traditional infrastructure, this might be an example of natural infrastructure for addressing a similar problem. This is what is sometimes described as one of the largest human-made wetlands in the United States, the East Fork Water Reuse Project. It draws effluent-dominated water from the East Fork of the Trinity River in North Texas, runs it through about 4,000 acres of man-made wetlands, and returns it into a drinking water reservoir for indirect potable reuse. So can we apply those kinds of ideas to what I'll describe as drastically disturbed watersheds? The Tar Creek site that I'm going to talk about today was the site of historic mineral extraction. What you see on the surface there are large piles of waste material contaminated with lead, zinc, cadmium, nickel, arsenic, and a suite of other trace metals. Impeded drainage in the waterways, really a massively disturbed landscape. And I would say that's a landscape that needs natural infrastructure. So if we take a little closer look, we still have open mine shafts on the landscape surface here, and I'll talk a little bit more about the history of this site in a moment. But you can see on the left-hand side, some folks standing next to a big hole in the ground that goes down into the underground mine workings. One of the problems is that at times those areas will take surface water. So during times of high flow, they'll take streams. That water gets into the mine workings, gets contaminated, and then in the middle photograph, it will re-discharge at under artesian head pressures downstream. And it's now contaminated. It goes out into the stream, as you see on the right. That orange color is evidence of iron oxidation, so one of the trace metal constituents. So a really kind of complex hydrogeologic phenomenon as well as an ecological problem. So the rest of the talk, I want to talk about some site-specific challenges at this particular location, our ideas on natural infrastructure that we've implemented over the last couple decades, a little about what that natural infrastructure has done ecologically. So a little bit about receiving stream recovery, and then I'll finish up with some conclusions. So what are the challenges that we face in these mining impacted landscapes? This, of course, is not where we're working is not necessarily unique in many ways. If you think about mining in the United States, you might think about the coal basins in the Appalachians or the mid-continent. You might think about the trace and base metal mining, or excuse me, the precious and base metal mining that went on is going on in the American West and the Rockies. But what a lot of folks don't realize is that right in the center of the country, Missouri, Kansas, and Oklahoma come together, was the largest lead zinc mining district in the world for much of the 20th century. So they mined lead and zinc in the tri-state in Missouri pre-Civil War. Mining didn't come into Oklahoma until the early 1900s, late 1890s, early 1900s. They were mining the sulfide ores of lead and zinc, galena and sphalerite. And this was an active mining area up until the post-Second World War era. Everything kind of was gone by the 1970s. All the mines were closed. These were big holes in the ground. So we're not talking about coal mines where folks are on their knees with a pickaxe. These were 60 to 100-foot ceilings, 150 to 400 feet below the land surface. You can see the circle there is a miner actually hanging on the wall of the mine, setting a charge. So very substantial excavations, and then all the material that they created came up to the surface to these massive processing operations. So those two photographs are of a community called Pitcher, Oklahoma in 1926, which was about the peak mining time. You can see those derricks sticking up out of the ground. Every one of those would have a mine shaft associated with it. The big piles are the waste materials. So they would process, take what they could, and leave the big piles on the surface. And then, of course, you can see the miner shacks out in the foreground there as well. So to spatially oriented us, we're in that northeast corner of Oklahoma, right where Kansas and Missouri, the borders are. Back in the day, these were called the Galena, Joplin, and Pitcher fields in each of the states. So the tri-state mining district. And folks mined the lead and zinc that helped win the First and Second World War. And there's still a bit of regional pride in the work that went on in this mining district way back when. The legacy of that work, of course, is substantial. And today, we now have 4 U.S. EPA CERCLA or Superfund sites in the tri-state mining district, 2 in Missouri, one in Kansas, and the Tar Creek site in Oklahoma. So the images there on the left, very large waste material piles on the surface and contaminated water resources. So significant environmental legacy of the work that went on there. And again, to make sure we're kind of on the same page before I delve deeper into things, anytime we do any sort of mineral excavation, when we have mining, no matter what we're mining, there's the possibility of producing poor quality water. And in very simple terms, those sulfide minerals are stable when they're underground. When we expose them to air and water and some helpful bacteria, we produce a sulfuric acid solution. So we're producing a solution that then results in increased mineral, carbonic acid, and proton or low pH acidity. That leads to a lot of different trace metals, depending upon what the geology is. We can have a suite of different trace metals in solution. We often have elevated anions, especially sulfate, along with a series of base cations. So a very, very concentrated solution then that you can imagine when that gets out into receiving water bodies can be detrimental to fish, macroinvertebrates, and the overall ecology of an area. So this is an example of one of the untreated discharges within this watershed. It is flowing by artesian head pressures from about 100 million cubic meter mine pool. So those excavations, those big holes in the ground they made, are now full of about 80,000 acre feet of polluted water. And under head pressures, it discharges with elevated concentrations of iron, zinc, lead, cadmium, nickel, arsenic, sulfate, and other things. This is that same image I showed you earlier, starting this part of the talk at a location called Douthit Bridge. It's right in the center of the mining district. The water on the left is evidence of artesian flows of those mine pool waters. Elevated iron concentrations, dissolved iron concentrations will oxidize and hydrolyze, making that rust color you see. But on this rainy day, when I took the picture, you can also see runoff from those big waste piles. So another source of polluted water into the stream with metals contamination. And then if you take a little closer look at the stream itself, it's actually full of mine waste. So over the decades, it has filled up with contaminated solid material. So we have multiple influences on what's going on in our receiving water bodies. This image is pretty typical for Ottawa County, Oklahoma. The trailer house you see there, background is about a 300-foot pile, 300-foot tall pile of waste material. So household income in that portion of our state is less than 2/3 of the U.S. median. Poverty rates are about twice the U.S. median. About 1/3 of the population are Native American, underrepresented groups. Back about 15 years ago, there was a targeted buyout and relocation of these mining communities. So if you're familiar with the way we handle risks, or when we talk about risk assessment, we often talk about sources and receptors. In this particular case, the decision was made to remove the receptors and not necessarily deal with the sources. So the sources are still having ecological impact, even if there's been a buyout of the human population. Our license plate in the state of Oklahoma used to say Native America. We've changed them since then. So this was Indian territory. And you might be familiar with the 5 civilized tribes that removed Oklahoma, the Chickasaw, Choctaw, Cherokee, Seminole, and Muskogee. But that little northeastern corner, that Ottawa County corner there, is actually home to 10 Native American tribes, some of which have lands in the hundreds to thousands of acres. So not great land holdings. And you'll notice the upper portion, the light green, the Quapaw Nation, their reserve lands include the underground mine workings in the Tar Creek watershed. So we have significant technical challenges on these sites, but also significant social, cultural, and economic challenges that have to be addressed along with the science and engineering work. So if you saw the abstract, the term irreversible damage was used in there. And back in 1979, after the mining ceased about 1970, it took about a decade for those mine pool to fill up and begin to discharge at the surface. So water first came out of the ground in 1979. Superfund was passed in 1980. Tar Creek was immediately examined and received listing on the first national priorities list in 1983. By 1984, EPA and the state had gone in and done some work, and they issued their record of decision on surface and groundwater. That says, this is the problem as we understand it, and this is our solution. And what they said was, we need to redesignate the beneficial use classification of the stream. So it is so damaged that by irreversible man-made activity, that we are essentially not going to do anything. And they use something called a fund balancing waiver under Superfund that says it costs too much to fix this problem. So from 1979, when those waters first came out of the ground, and after the 1984 Operable Unit 1 Record of Decision, there's been no comprehensive attempt to treat these polluted waters. My team, the Center for Restoration of Ecosystems and Watersheds at OU, started working there in 1997. We do work, we're mainly a water quality team, but we look across different water sources. We do soils and sediments and some biotic sampling. We began to try to understand the problem here, this irreversible damage. The map on the right, the black areas are an extent of the underground workings. I had a doctoral student develop this map. He actually did a 3D rendering now. We have a 3D model of those underground workings so we can understand the flows. But there were 3 areas where the bad water was coming out of the ground. 3 areas that we identified as being of significance. We chose to sample what we call the unnamed tributary watershed. You see it in the southern portion of the watershed there. The idea was that this was a part of the pie that we thought we could bite off and chew. And we really focused our efforts on this idea of natural infrastructure, what we call passive treatment. So the question we were trying to get at was is this true? Are these truly irreversible, especially now, 46 years after those flows began? Is this a problem that is unsolvable? Obviously, engineers can do a good job of addressing these problems. Good engineers can design what we call active treatment systems. So chemical addition, active aeration, lots of steel, lots of concrete, burning of fossil fuels, significant capital, significant operation and maintenance expenses. And in an abandoned site or a derelict site like this really isn't an option. And it's one reason why the Record of Decision says that the problems are unsolvable. But if that's active, perhaps there are passive technologies that look at natural biogeochemical, microbiological, and ecological processes that are driven by renewable energies that do have some capital expense in the design and construction, but their operation and maintenance costs are going to be substantially lesser in the long term. And that's kind of where we focused our efforts. The idea of building natural infrastructure to address these problems. And that area is one of the systems I'll discuss. This is the Mayer Ranch passive treatment system. During a managed drawdown a couple years ago, you can see multiple process units there. That is based upon about a decade of laboratory experimentation, pickup truck chemistry, bucket experiments out in the field. And what we learned from all that work was that given the suite of contaminants in these waters, we really couldn't build one system to treat it. We need targeted removal of different things by different mechanisms. Some are oxidative, some are reductive, etc. So we came up with ideas for sequential process units. Based on our understanding of the hydrology and geochemistry, we're going to build specific ecologically engineered process units to address the polluted water. So reorient ourselves. There we are. That's that northeast corner of Oklahoma. The yellow outline is the boundaries of the Superfund site. The white blotches on the satellite image are those waste piles. So you can see them from space. The orange line is the main stem of Tar Creek. Flows right through the middle of the mining district into the Neosho River. I also want to point out on the south side of the Neosho River, Coal and Cow Creek. Those are reference sites, and I'll come back to those later on. They're unimpacted, unmining impacted references for us. But again, our major focus is on that unnamed tributary site, the study site in the kind of red dotted box there in the lower or southern portion of the watershed. So this is a portion of that unnamed tributary watershed. You can see the stream on the right-hand side. We are very near Commerce, Oklahoma, home of the Commerce Comet. If some of you pay attention to baseball history, Mickey Mantle grew up in Commerce, Oklahoma, and had that nickname. You can see some yellow dots. Those are our long-term sampling locations. So we had 2 areas where mine water was discharging to the surface. Southeast Commerce in the upper left, And there's a big orange subsidence feature there where the ground had caved in. And then Mayor Ranch in the more toward the lower right, those yellow dots. Right on the other side of historic US 66. So that's the mother road that flows right through the middle of our sites. This is 2003 when we were collecting data, both at the discharges and then on the unnamed tributary. By 2021, we had designed and constructed and began to evaluate 2 full-scale passive treatment systems, Southeast Commerce and Mayor Ranch. We have multiple locations of sampling water quality and quantity within the systems as well as in the unnamed tributary. So a very robust data set to try to understand the performance of these systems. If we look a little more detailed, this is the Mayor Ranch system funded by US EPA. It's been working continuously for 16 years, since November of 2008. Multiple process units, in this case, parallel treatment trains, 10 process units, some of which are oxidative, like the oxidation pond and the surface flow wetlands, some of which are reductive, like our vertical flow bioreactors, which we then follow by re-aeration ponds and some polishing units. But again, sequential process units, some redundancy built into this design with the parallel treatment trains, because we wanted this system to demonstrate the technology up front. We treat about 420 liters a minute here. Wetted surface area is about 2.25 hectares. The system works. So these are summary data over that lifetime, increases in pH, and substantial decreases in iron, zinc, lead, and cadmium concentrations. Some of those going below our practical quantitation limit. We can't measure them in the laboratory. And what that means is that this system is retaining significant masses of the contaminants of concern. So if they're retained within the system, they're not entering the unnamed tributary, they're not entering Tar Creek, they're not entering the Neosho River, and they're not working their way down into downstream reservoirs. We demonstrated success at Mayor Ranch, and in 2017, we're able to move across the street and address the Southeast Commerce discharges. Funded by the state of Oklahoma, the Oklahoma Secretary of Energy and Environment, and the Department of Environmental Quality. This system's been online for about 8 years. Much simpler. We learned a lot at Mayor, so now we're down to 4 process units. We're actually treating, and similar process units, oxidation pond, surface flow wetland, vertical flow bioreactor, and a final polishing unit. We're treating more water, about 600 liters a minute, in a smaller footprint, about 1 hectare at this site. And performance has been very similar. Increases in pH, decreases in iron, zinc, lead, and cadmium, and again, substantial mass retention of those contaminants before they get into the receiving water body. So I want to just briefly delve a little bit into the 2 workhorses of the system. Some of these process units are oxidative, and in those, we're trying to get air in the water. We're trying to oxidize, hydrolyze, and precipitate iron and make that orange sludge. Turns out that material has a very active surface. It does a great job absorbing some trace elements like arsenic, lead, and cadmium. Given that we're working in Oklahoma, we have to use off-grid aeration. We have to aerate the water effectively to promote these processes. Unlike working in some place, perhaps like West Virginia, where we could run the water down a mountainside, we're pretty flat. So we do that utilizing solar and wind power. We use solar and wind to run aerators to push air into the water. If these systems work, they're going to accumulate that material. So we're also exploring some potential resource recovery that I'll get back to before I'm done. Some data, Mayor Ranch and Southeast Commerce, inflows on the left, outflows on the right, dissolved and total iron on the y-axis. So you can see the big decreases in the bars occur in those oxidative process units up front. And there actually is data in those latter process unit effluents. I'll blow it up there. And you can see that our dissolved iron concentrations leaving both of these systems go from close to 200 milligrams per liter down to about 0.2 dissolved iron that we discharge into the environment. They were designed at 20 grams per square meter per day iron removal. And over the course of time, they're removing somewhere between 20 and 27 grams per square meter per day. The material, these systems are designed they're going to fill up with that stuff. So The upper right image, I know the numbers are probably very small, but those are depths of accumulated wet sludge that we can go out and core. And that's the core samples you see in the bottom. If we collect those, we bring them back to the laboratory, we can do scanning electron microscopy. We find an amorphous ferrihydrite precipitate in the surface samples, but deeper in the cores, we are forming a crystallized goethite, a less bioavailable, less mobile type of iron precipitate in the deeper cores or the deeper portions of our cores. So we're accumulating a less mobile, less bioavailable product. The other big process unit are the vertical flow bioreactors. So in these, we're flipping the redox scale. Where we wanted to go oxidative up front, now we're going to go reducing. And these are a little bit more engineered. So the upper left photo is a perforated network of piping. So a drainage layer that then in the lower photo below that gets covered in gravel. So we form a drainage layer, which we then cover with an organic material. And in our case, we use mushroom compost. It is a locally available product. We got a mushroom farm a couple miles away. It turns out that it has tremendously appropriate carbon-nitrogen ratios to promote bacterial sulfate reduction. So in these units, we're trying to bring that water in on the surface. We want to make contact with the compost where the microbes will reduce sulfate to sulfide, which then immediately interacts with cadmium, lead, zinc, nickel, and forms insoluble metal sulfides. Then the water goes into the drainage layer and flows out the bottom. So similar type of plot for water quality information. You can see some changes in zinc in the oxidative units, but the big changes occur with the vertical flow bioreactors. That's where we see the dominant removal mechanisms. We can do the same thing in these systems, go out and sample those substrates, collect the organic matter that's been accumulated over time. And I should mention in the top photograph there, that's one of those sites in operation. It looks like a pond. You wouldn't know all the engineering that's going on under the surface with the drainage layer. But if we collect those substrate cores, we can bring them back to the lab, do sequential extractions. This plot of a series of metals on the x-axis and the percentage distribution on the y. And the only thing I want to point out is the predominance of the purple. That's the sulfide fraction. So they were designed for sulfate reduction, designed for metal removal with sulfides. And these data say that we're forming sulfides. And again, we can do our SEM work, our scanning electron microscopy, and we do find zinc sulfide colloidal aggregates within the substrate, as well as pyrite. We're forming framboidal pyrite iron 2 sulfide within the VFBR substrates. Again, less mobile, less bioavailable fractions of those trace metals. We did do some interesting design innovations at the second site. We are very near the high school for the City of Commerce in this work. We were worried about excess sulfide. We were worried about the stink problem, if you will. Sulfide, of course, stinks like rotten eggs. This is our odor control system. So the pipes that you see on the right-hand side flow water out of the vertical flow bioreactor, but the smaller diameter pipe going back to the left is pooling the atmosphere out of the odor control system into, I think you can see my mouse, this black pipe here, which is an activated carbon filter. And we run all that with solar power. So we're running a vacuum pump to actually pull the sulfides off the surface, strip the hydrogen sulfide out of the air. We also use those same solar panels and batteries to aerate, both in the initial oxidation pond as well as in the final polishing pond. So we've been working there since 1997. We obviously wanted to get a good handle on flows and chemistry when we started. We installed this weir in 1997 at Mayor Ranch. That's what it used to look like, nice orange water going over it. That's what it looks like today. The water that we discharged to the stream. That's what the discharge looked like before we started working. That's what the discharge looks like today, where we discharge back into the stream. At the Southeast Commerce site, this is the headwaters of the unnamed tributary, pre and post implementation of the passive treatment. So I'll ask you, is that water irreversibly damaged? Well, We've also looked at what's going on in the stream itself, what's happening in the receiving stream. So we have multiple locations along the unnamed tributary where we've sampled water chemistry, as well as regular fish community collections and some macroinvertebrate work as well. That are numbered from 4 to 1 from upstream to downstream, as you can see, kind of bracketing where the mine drainage comes in into the system to help us understand not only the chemical quality, but the biological quality. So if we look at the chemistry, this is 20 years worth of data at 2 of those sites, UT1 and UT2. They're the ones that are downstream of both passive treatment system discharges, iron on the left, zinc on the right. You can see a lot of variability pre-implementation. There's a lot of influence from, excuse me, from rain events, etc. After Mayor Ranch went in, we see a statistical decrease in those concentrations within the stream itself overall. After Southeast Commerce went in, we see an even greater decrease in those concentrations. So much so that between 2017 and 2024, every sampling event met the acute and chronic in-stream aquatic life criteria for cadmium, lead, zinc, and iron. So I can talk about chemistry all day long, but the thing that gets at least the lay person excited of our work is the work we do with fish. We sample fish by seining. We're unable to electroshock these waters because the conductivity is so high that it doesn't work. Some fish data. This is UT1 location. Pre-2005 to 2007, the system was built in 2008, and then post-2009 to 21. The big take-home here is not only the catch per unit effort changes, but the fact that our species richness is almost doubled. We've gone from 8 to 15 species of fish, including some relatively sensitive species, including blunt-nosed darter, a number of catfish and crappie, sunfish, and bass species. Similar type of changes at UT4, that most upstream location after the Southeast Commerce system went in. We've gone from 4 to 20 species over the last few years since implementation of the passive treatment system, including, again, a number of relatively sensitive species. So we've done no in-stream habitat restoration in the water body, in the unnamed tributary. All we've done is improve source water quality, and we see the return of the biological integrity. Not an investment in riparian restoration, no investment in stream bank stabilization, simply an improvement in water quality. The habitat is adequate if we can clean up the chemistry. Just a couple other. I want to walk downstream through those sites. This is UT4. The top 2 figures are some data of iron and zinc, and you see overall decreases over the 2 time periods. The bottom 2 figures are species richness and diversity, and we see increases in both corresponding with the decreases in metal concentrations. We didn't sample this prior to the construction of Mayor Ranch, so we only got 2 time periods here. This is UT3. We can see some variability in iron and zinc up there, and that's another story that if you have questions about, I can tell you. But we do see overall increases in richness and diversity at UT3 over the course of the implementation of the passive systems. UT2 decreases in iron and zinc, but notice in our fish data where we see increases in richness and diversity, we lose a time period. We don't have any data for the most recent past. And I'll tell you why that's in a reason why fish sampling was not practical after 2016. And then here's UT1. Again, decreases in the trace metals concentrations and increases in richness and diversity, demonstrating the utility of the natural infrastructure implementation. We know that there can be variability in those fish populations within natural streams. We live in Oklahoma. We're in the Great Plains. We have significant climatic cycles, droughts, and floods. A lot of variability in Cow and Coal Creek, the 2 reference sites. A lot of variability in the main stem of Tar Creek. However, if we do some non-dimensional metric scaling of these data for those different time periods, we see in the reference sites, they all kind of overlay one another. So there's no statistical difference. If we look at it for our UT sites, they begin to separate out. So the black is the most recent data. The red is the after Mayor Ranch before Southeast Commerce, and the blue is the pre-data. So the blue kind of separates out there at UT1. It kind of separates from the black at UT3, definitely separates at UT2 and UT4. So we do see significant changes in those fish community metrics within the stream. This is that UT2 site. The reason we couldn't sample it after 2016 was because it was no longer a stream. It became a wetland. It became a pond wetland. It was so deep that we couldn't get in chest waders and do our fish community analyses. And part of that was because of this guy. So this the system went in 2008. I think you can see him right there. We hadn't seen beaver in the watershed until 2013. 2013, we started to see beaver recolonization occurring. And now on our wildlife cameras, we pick them up on a regular basis. We got beavers coming. We got beavers going. They have taken that weir that I showed you earlier and helped us maintain it. They built a beaver dam on top of it. We fought them for a little while. We'd tear out the beaver dam and it would be rebuilt by the next morning. So our long-term monitoring station at the weir is now a beaver dam. We allowed them to take it over. A few years later, we picked up this on our wildlife camera, the return of North American river otter, Elantra canadensis. So these guys were extirpated in the state of Oklahoma in the early 20th century. They were reintroduced in the 1980s, about 200 or 300 miles south of us. We had not seen any evidence of river otter in this drainage. Now we pick them up regularly on our wildlife cameras. Now I'm not a wildlife biologist, but what I've read is that that otter will recolonize abandoned beaver lodges. They also require clean water. So it's a system. Everything is connected. Water quality improved. We see changes in chemistry. We see changes in the fish community based on those changes in chemistry. We see return of North American beaver, and then we see recolonization of North American river otter. The system is connected. If we can clean up the problem, that problem is not irreversible. Or I would argue that that problem is not irreversible. Even within the systems, we see significant changes. We see significant changes in discharges back out into the environment. So what comes next for us? We built two systems in an unnamed tributary watershed. We're looking at Beaver Creek. It is a culturally important water body for the Quapaw Nation. We have ongoing work with the state to look at these seasonal, much larger flows at the Douthit area. We'd like to see that stream run clear. We're doing some novel environmental monitoring, not only the homemade catamaran you see up there in the upper left where we go out and sample soils with, but we're flying small and unoccupied aerial systems. We do a lot of field work. This site is about 3.5 hours away from my university. If we can collect environmental data more efficiently, we're all for it. So these data are that Mayor Ranch oxidation plot on the left is real data, going out and taking samples. On the right are data generated by spectral reflectance of our cameras on our unmanned aerial systems that allow us to predict water quality. And on the right are the residual calculations. But we're able to be more efficient in our data collection. I mentioned that these systems accumulate this stuff. This is they're designed for metal accumulation. Their process lifetimes are 20, 25 years. We've begun to explore this material. We were able to pump the sludge into geotextile bags. We end up with a product that looks like this. Remember that it has a very active surface. And sure enough, if we manipulate the pH and the point of zero net charge appropriately, it is actually a really good phosphorus absorptive agent. On the right are local sediment numbers for phosphorus absorption, about 700 milligrams per kilogram. Our mine drainage residuals are about 35,000 milligram per kilogram. They take up a lot of phosphorus. All right, so to wrap it up, properly designed and sized passive treatment systems are demonstrated natural infrastructure solutions that improve mine water quality. I'm very confident in saying that. And improved water quality has direct influence on the ecology. However, widespread applicability of these ideas requires revisiting and revising some of the administrative and regulatory constraints. So one of the things under Superfund they do is they go in every 5 years and evaluate things. In 2000, they said the massive costs associated with addressing surface water means we don't need to revisit that 1984 OU1 ROD. We built the first system in 2008. They said passive treatment appears to be feasible. It may no longer be a valid approach to use that OU1 ROD. By 2020, they're considering opportunities in the expansion. None of these statements have come with any resources to do anything new. We're waiting for the 2025 five-year review statement. I will say, if you're interested in this sort of stuff, there's a group called the Network for Engineering with Nature. I know the University of Florida is a member of NUN. It's the idea of working together. Nothing is irreversible. And with that, with my name and phone number there, I will be happy to answer any questions if we have time. Thank you.
Thanks, Bob. That was great. It's great to hear a feel-good story every once in a while, especially these days. So it's really nice to see the results that you're getting there and the collaborations you've had across different agencies and tribes and students and funders, and hopefully you'll continue doing it. So we have about 7 minutes for questions. We'll start in the room and then I'll go to YouTube and see if we have any from there. So questions for Dr. Nairn. Go ahead, AJ.
So I have two questions. I don't know if you can hear me. I need to scoot up a little bit, sorry.
You're good.
My first one is when you're thinking about restoring a system back to something or thinking about something, it's irreversible. We talked about this a little bit in David's class last semester and wetland restoration, like restoring it to what and like what is actually feasible. Thinking about like the I mean, I guess like I don't have like too much information on like pre-mining and like how the system work. You don't have like a lot of detailed data about that, but when you say irreversible, like you did, I guess, like double the water quality and things of that sort, but like thinking about pre-mining conditions, do you really think that it's possible to get like to pre-mining conditions or just get better conditions? And if that is like in the scope of irreversible, if that makes sense.
Yeah, you know, one of the questions I talk about this in some of my classes too is, you know, what is the endpoint, right? What do we, when we talk about pre-restoration conditions, what does that really mean? How far back are we going to go? You know, and in this particular case, I think one of the important things to remember is that these lands were allotted to Native American tribes that were not necessarily native to those lands. They were removed to Oklahoma, but they still have a cultural importance to those tribes. So that is a factor that we need to consider when we think about ultimately what do we want this landscape to look like, because those are treaty lands that they have that are theirs. I think one of the things I did not talk about, but that if you're interested, I can send you some information on. One of the other big success stories at this site is that up until 2013, most of the land reclamation work was being done by private contractors through EPA. And in 2013, EPA let the first tribally led Superfund remediation contract in the nation. The Quapaw Nation got some money from EPA to clean up one of their tribal trust lands. It was a site called the Catholic 40 acres that the Catholic Church had owned, had a mission school on it, and then had allowed mining to occur. They did such a good job. The Quapaw Nation now leads all land reclamation activities at this site. They are doing about $25 million a year of land reclamation work. They don't do water because the OU1 ROD still says this is irreversibly damaged, but they clean up the land and they're putting it back into the land uses that are appropriate for the tribal nation. Today, that does not mean what was there pre-mining. It means mainly pasture and other agricultural production. And that's what they want. They're putting it back into the land uses that are most appropriate for the tribal needs.
Thanks, Bob. Other questions from the room?
Okay, because I got another one.
Okay.
Okay, I was gonna ask you how you feel about this work. I know like this is like 10+ years of work that's been like done almost. How are you feeling? Like, do you feel like accomplished by this? Like, do you like think about next steps? Like, you know, are you all like giving talks to like kind of apply these to other areas, or I guess other, there's a huge areas of thinking about, kind of taking this information and kind of applying it to other places that need restoration in the area? Like, how is this kind of like being communicated to, I guess, your immediate community?
Yeah, so everything that we do, everything that crew does, I would say is number one, it's service learning oriented. Everything we do in our research team and in our classes. And secondly, everything we do is community engaged. So we work very closely with not only the tribal communities, the nation in this particular case, but with local municipalities, counties, local landowners. Everything we do is on private land. So we're very much cognizant of the need for that kind of community communication, regular open houses, regular meetings with folks. So we try to do the best that we can to communicate our science effectively, not only to the local populace, but to decision makers as well. The first part of your question, yes, we have taken this elsewhere. We've done a great deal of work in South America. I've got some active research in Bolivia. Some mining areas have been mined for about 500 years. Some of the worst water I've ever sampled in my career, terrible concentrations. But we've been able to work with Quechua and Amari people in Bolivia on historic mine water influenced problems and implement some of these similar ideas elsewhere down there.
Thanks, Bob. We have two questions from YouTube from someone at Wetland Solutions. I don't know if we think this is Scott or Chris, but we have a question about, have you experienced clogging within the vertical flow wetlands? And also, have you done any biological sampling within the treatment units themselves?
So the answer to both questions is yes. We've done two major maintenance, what I call rehabilitative maintenance activities at the Mayor Ranch site, the older site, the 16-year-old site. We did start to see some hydraulic conductivity problems in the vertical flow cells. We drew them down. We flipped the substrate, essentially remixed the organic matter, and we were able to recreate the original hydraulic conductivity. That occurred about year 10. So that system's 16 years old. So about year 10, we flipped the substrate. We're back to the original hydraulic conductivity. We've not seen that start to creep again in the last 6 years. We have done a substantial amount of work within the systems, mainly focused on vegetation and macroinvertebrate communities. A little bit of amphibian monitoring, a little bit of bird monitoring. But vegetation-wise, the above ground biomass is less than 1% when it comes to metals concentrations. There may be some influence, but it's pretty minor. Most of this is happening in the subsurface, in the soils, in the substrates. Macroinvertebrate communities are in our downstream process units. Diversity and richness is equivalent to our reference sites. So we see an improvement in macroinvertebrate community structure with downstream flow through the systems. We've got some data on amphibs and herpetofauna and birds as well. It's an ongoing effort to try to understand, the potential. We don't want to create an undue risk, obviously. So we want to be cognizant of that and want to monitor that over time.
Yeah, so following up on that, just thinking about even, thinking about sampling and protecting your students and workers and also just the nearby community. So has there been a perception or perhaps a quantification of any increased human health risk? Because you're making like an accumulation zone, right? Like that's how it's working. You're accumulating materials and cadmium and zinc and lead and iron. So how do you manage human health risk?
So neither of these sites are publicly accessible. There's restricted access. They're on private lands. The state and the university are pretty much the only folks that access. They're fenced, et cetera. One thing I did not touch on that perhaps I should have, in the bigger picture for the mining district, there were some significant, back in the mid 1990s, elevated blood lead concentrations were found in about 35% of the children in this watershed, which is absolutely terrifying. Today, that number is down to about 2%. And that is a great deal of credit that goes to the local county health department, did some substantial education efforts, as well as a lot of the land remediation work that is currently being done by the Quapaw Nation.
Thanks. Any last questions for Dr. Nairn? All right, one more round of applause. Thank you, Bob. Appreciate it.
Thank you all again. I appreciate the opportunity.
I very much would hope to see you here in another couple of years with the updates on the next round of installations and updates on how these systems are continuing to work. So we'll be back in touch.
Sounds great.
All right, thanks
Sounds great.
everyone. Next week we have, let's see, CFW. I try to pull this up ahead of time. Next week, our speaker is, our own Dr. Jim Jowitz from Soil, Water, and Ecosystem Sciences. So it'll be an in-person seminar next week, and we'll see you then. Thanks, everyone.